Hello, everyone. Welcome to another episode of Cuda Education. Today we are on step 10 and it's cascaded shadow maps. So, of course, high level overview. Um, not getting into the weeds right now. We're just trying to get through all of our steps. Last time I checked, it's 16 steps. So, we are at step 10. So, step 10 is cascaded shadow maps. But before we get into the summary, we need to know what cascaded shadow maps is. Now, the result of this step is this guy right here. So we could see some improvement um, in our scene, notably that we now have shadows for this barrier right here. And we just see some improvement in the building in terms of the shadow and also just the building itself, and just how things are displayed. So there is some improvement, obviously, mostly dealing with shadows, but this seemed to be an involved step with a lot of things going on. But we want to figure out what is cascaded shadow maps before we get into the summary and all the changes and stuff that happened, right? So cascaded shadow maps is a technique for rendering shadows from a directional light like the sun across a large scene without running out of resolution. The core problem: a single shadow map has finite pixels, 2048 by 2048. If you try to cover the entire camera frustum, the view area, near equals 0.1 to far 1000, the shadow map text cells near the camera are stretched across huge screen areas, producing blocky, aliased shadows close to the viewer, exactly where quality matters most. The solution: split the camera frustum into multiple depth ranges, cascades, and render a separate shadow map for each one. Each cascade covers a smaller volume of the scene, so its shadow map resolution is concentrated where it's needed. So Cascade 0, from this range 0.1 to 7, high detail close, right? Cascade 1, 7 to 37, medium detail mid range, and then Cascade 2, 37 to 150, low detail distance. So you see, you have your near and then you have your far, obviously from the perspective of the camera, right? So Cascade 0 covers a small area near the camera with high detail, right? So you could even look at, this is about 7 spaces, this is about 30 spaces, and this is about over 100 plus spaces. So you could see that for the close area, it's a small contained area, and you could pile in more pixels and resolution and all of that into it, because and we want that because we want high detail. But of course, in the farther regions of the scene, we don't really care about the detail as much, right? Covers small area, covers mid-range. So Cascade 0 covers small area with near the camera with high shadow detail. Cascade 1 covers mid-range with moderate detail, and Cascade 2 covers far away with low detail, acceptable since it's distant. Each cascade owns its own orthographic projection from the light's viewpoint, tightly fitted to just its sub-frustum. At runtime, the lighting shader checks each pixel's view space depth to decide which cascade to sample from. In our implementation, we have 3 cascades, each 2048 by 2048 depth texture, stored as array slices. Splits computed via the practical split scheme, a blend of logarithmic and uniform spacing that avoids wasting resolution. Shadow range capped at 150 units. Beyond that, no shadows. They'll be too low res to matter. Okay, so that is the battle that we're fighting, and here is our summary. So step 10, cascaded shadow maps, which we just went through. Goal: add directional sun shadows using 3 cascade shadow mapping. A depth texture array is rendered from the light's perspective, then sampled during the deferred lighting to attenuate diffuse plus specular. Okay, and then we get into all of the details. Don't worry, guys. In the future, in future videos, we will dive into this stuff in more detail. Right now, we're just trying to see what's going on and see how the code changes until we get to our modern renderer project, our full-fledged project that is freely available on the Apple Metal sample code library. It's called Modern Renderer, one word. And we started with a fresh Xcode project with nothing in it, blank, basically. That's step 0 or step 1, and then we go all the way to step 16. So we're at step 10 now. So here are all the modifications. APL shadow types.h header file. We have a bunch of stuff happening here. We have APL simple.metal. Obviously, this is a shader, so it's on the GPU instructions. And you can see you have a bunch of stuff happening here. APL renderer.mm. That's a main source file on the CPU. We can see a lot of things happening here. Load with metal view, set up load with metal view per frame, draw in MTK view. We have 3 shadow render passes, 1 per cascade array slice, front face culling, reduces acne, depth, bias, renders all opaque, lighting, pass updates, all of this stuff. Render pipeline 4 passes. So we have our 3 shadow passes, depth only from light into cascade slices, depth pre-pass plus G buffer fill, and deferred lighting. Now sample shadow map for attenuation. Key techniques. Practical split screen, PSSM, balances near field detail versus far field coverage. Hardware PCF via sample compare, free 2x2 bilinear shadow filtering, front face culling plus depth bias, dual strategy to eliminate shadow acne, near plane extension, ensure shadow casters behind the camera, frustum still cast shadows. So that is it, guys. This is step 10. We have our result here, and we're gonna keep it moving. So next step is step 11. We're on the road to step 16, where we should have a full-fledged application, just like what is in Modern Renderer in the Apple sample code library. This is Cuda Education, guys. You know what to do. Thank you for watching. Have a great day.